All right, it's Mr. Shrum, and right now we're going to look at wave behaviors. Let's get started. We're going to describe reflection and interference of both sound and light waves and the refraction and diffraction of light waves. So, introduction. One summer evening, you and your friend Paul are at the park, sipping cold soda through a straw. You happen to notice and look at your glass. You see how this straw doesn't line up with the straw beneath it once it enters the water. Why does that appear that way to your eye? It looks bent, but then you take the straw out, it's perfectly straight. Paul begins talking about his recent trip to the Grand Canyon. Like many tourists, Paul couldn't resist screaming out his name from atop the canyon to hear the mountains echo his voice back to him. So, looking at these two situations, what is happening? What is happening with the light waves? What is happening with the sound waves? Light waves in the first scenario and sound waves in the second. We'll explain why this is happening in a few slides. Waves in one dimension. Mechanical waves travel through a medium, such as a spring, air, or water. Even electromagnetic waves can travel through a vacuum, and they can also travel through mediums like air or glass. When a wave encounters a boundary between its medium and another medium, factors like speed and amplitude often change. A wave might also be reflected away from such a boundary. These effects are called boundary behaviors because they occur at the boundary between two mediums. In addition, two waves traveling in the same medium can encounter and interact with each other. So we have a lesson activity. Back to that simulation, launching the wave on a string. I'll click the simulation. Select pulse and fixed end. I'll hide these meeting controls. Use the slider to reduce damping force to 0, then click the green pulse button to begin the simulation. Observe the behavior of the wave that is created when you pulse the button. At any point during the simulation, you can pause the simulation by clicking pause and play, and to reset. Okay, so let's see. Well, interesting. After I clicked the pulse button, a triangular wave pulse started traveling through along the string to the right. And then when it hits that fixed end, the wave turned upside down and traveled in the opposite direction. Other than the change in wave direction and turning upside down, there's no change in the wave after it hits the fixed end. The speed of the wave remains after it hits the barrier and inverts. Now take a look at what happens when two wave pulses run into each other. Press the reset button and then click the pulse button to generate a new wave pulse. At the precise moment when the wave hits its originating point again, click pulse again to create a second wave pulse. Do this through several cycles and observe the resulting wave. What do you observe about the interaction of the two waves? So we'll restart. 1, 2, oh, whoops. Have better timing. Here, I'll do slow motion. This is cheating. Not really. But here we go. Try to get it to line up exactly. Wham. One more try, and then I'll quit. There we go. I think it's about as close as I'm going to get for now. But what do we see happen? When the second wave is created at the same time, the crest of the two waves are aligned and a new wave with increased amplitude is created. So it's bigger, taller waves. And if you keep doing that, it just keeps going. But yeah, that's fun. And then last part, well, not quite the last part. When the two waves meet, they merge past through. When the pulse hits the fixed end and starts traveling in the reverse direction, click the pulse button again to create a second wave pulse heading toward the first wave. Okay, so restart. Bam. So start one, wait until it reverses, and then do another. Whoa. It like pushed each other back. Let's see how it describes it. They merge, pass through, and then continue to move in their respective directions. After the two waves pass through one another and move off individually, do you observe any change? No, there's still no change in the amplitude and speed. Da, 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 da. Anyway, when the two waves run into each other, they appear to merge at one point. When they are about at the same place, they seem to disappear entirely, but then they reappear. They must cancel each other out in some way. So we're going to look at behaviors like that. Wave reflection. So when a wave is traveling in a medium and then it hits a barrier, the wave inverts or turns upside down and starts traveling in the opposite direction. That is called reflection. Keep in mind that a wave is always reflected back from a boundary in the medium. When you see your reflection in the mirror, which is metal-coated glass, or in a swimming pool, water, you witness the behavior of light waves at a boundary. Recall that the speed of a wave traveling in a medium remains unchanged, so the speed of the reflected wave remains the same as that of the incident wave. You also know that the wavelength of the reflected wave depends on its speed. Because there is no change in the speed of the reflected wave, its wavelength also remains unchanged. Note, however, that the amplitude of the reflected wave depends on the boundary of the medium. Superposition and interference. So in the simulation, you observed two waves traveling in the same medium and then running through each other. That is called interference. That affects the displacement of the medium where the two waves pass through each other, but does not change the waves' velocity or direction. After this interference interaction, the two waves continue to travel along their original path with their original amplitude. The principle of superposition states that the displacement of the resultant wave at the point of interference is the sum of the displacements of the individual waves. The diagram above demonstrates how the two waves in the simulation add up to the combined waveform you observed. Before interference, during interference. Recall that the two waves are in phase when their crests are aligned or on the same side of the equilibrium line as shown in figures 1 and 2. The interference of two waves that are in phase result in constructive interference. So in figure 1, it shows two waves of equal amplitude traveling toward each other in the same medium, and they're in phase. The second figure shows the point at which the two waves overlap. According to the principle of superposition, the resultant displacement of the two waves at the interference point is the sum of their individual displacements. So it's twice the displacement of each wave. Note that in constructive interference, the resultant amplitude at the point of interference is always greater than the amplitude of either individual wave. Their displacements are added up. Now let's consider destructive interference. Destructive interference occurs when two out-of-phase waves meet. Figure 1 shows two waves of equal amplitude but opposite phase traveling toward each other in the same medium. One wave has displacement A, while the other has a displacement of negative A. So one's over here and one's over here. And they cancel each other out in this type of interference. The positive crest overlaps with a negative trough, and if you add a positive to a negative, you get 0. This is destructive interference. The resultant amplitude of the point of interference is always smaller than the amplitude of either individual wave. So we're going to look at a problem now, and using the principle of superposition, let's solve these interference problems. Two waves, A and B, have equal wavelength and amplitude of 100 units and 50 units, respectively. They interfere with one another when they are in phase. What is the amplitude of the resultant wave? Which type of interference is this? We know the A amplitude is 100 units and amplitude B is 50 units. We need to find the resultant amplitude R. Well, R is A plus B because the two waves are in phase and they will constructively interfere. The waves are in phase, so this interference is constructive. So it's just 100 plus 50. That is 150 units. Problem 2. We have wave A with an amplitude of 75 units and an amplitude of periodic wave B, 50 units. Both have the same wavelength. If the two out-of-phase waves interfere, what is the amplitude of the resultant wave? Which type of interference is there? We know that amplitude A is 75 units, amplitude B is 50 units. We need to find the resultant R. Well, they're out of phase, and according to the principle of superposition, we have R equals A plus a negative B. 75 plus negative 50, that is 25 units. So 75 minus 50 equals 25. Because these waves are out of phase, the interference is destructive. The amplitude of the resultant wave is less than the amplitude of either wave on its own. So checkpoint Two pulse waves, A and B, arrive at a point in a medium simultaneously. If the amplitude of wave A is 35 units, the amplitude of wave B is 41 units, and the two waves are in phase, what is the resultant wave amplitude at the point of interference? Well, in phase means that this will be constructive. So you add 35 and 41. Then we're going to talk about transmission. When a wave on a spring reaches a fixed end, the wave is reflected and inverted. Now consider a light spring connected to a heavy spring. The heavy spring is a slower medium, and the light spring is the faster medium. A longitudinal wave from the light spring travels along until it hits the boundary where the lights and heavy springs meet. The wave is partially reflected back to the light spring and partially transmitted into the heavy spring. Wave speed is determined by the medium. Since a reflected wave stays in the same medium, its speed is the same before and after the reflection. Also, recall that when a wave is reflected from a fixed end and the reflected wave is inverted. A wave from a light spring is also inverted after it reflects off a boundary with a heavier spring. Because some of the wave energy is transmitted into the heavy spring, the amplitude of the reflected wave is lower than the initial wave. The partially transmitted wave has a different wave speed in the new medium. In this example, the wave travels from a faster medium, the light spring, to a slower medium, the heavy spring. So the speed of the transmitted wave decreases. If it were a periodic wave, the slower speed would also decrease the wavelength. The heavy medium is initially at rest, so any displacement from its state of rest will be in the direction of the original wave. Therefore, a transmitted wave is not inverted as a reflected wave is. So reflected would be opposite. Transmitted pulse would not be. It would be in the same direction. But I'll stop there, as that's the end of waves in one dimension, and we'll look at waves in 2 dimensions next time. But until then, stay safe, and I will see you guys next time. Bye-bye.